Hello, IME 146 students. Welcome to our week 4's lab presentations. This week, we're going to go ahead and talk about non-traditional machining processes. And specifically, we're going to talk about 3 of them. We're going to talk about chemical milling, electronic discharge machining, and then laser cutting. And then in week number 4 of your lab, or actually week number 3 of your hands-on lab experience, you're going to be doing some laser cutting. So you're going to be using the laser cutter to cut out that Geneva wheel for our assembly that we're creating together in the lab, right? We're going to go ahead and cut out this complex part. You can kind of see it right there with the laser cutter right there. But before we get into that, we're going to learn all about the non-traditional machining processes. So far in IME 145, you were exposed to the conventional machining processes. If you remember, those conventional processes all shear to chip off the workpiece. So they're using shear stress to shear chip off the workpiece through sawing, drilling, milling, turning, and broaching. Well, we're going to talk about the next set of processes, the abrasive processes, after we cover the non-traditional ones. So the abrasive processes actually came second. Well, we're going to jump ahead, though, the non-traditional processes because we need to learn about them in order to make the parts in the lab using those processes. So we'll cover abrasives, I think, about week 6. So we have 2 weeks, 4 and 5 on non-traditional processes. And then week 6 will be abrasive. Week 7 and 8 will be a production air motor thing that we're going to do together in our presentations here. So those non-traditional processes, they are going to use other types of energy out there. So those traditional machining processes, they removed material by shearing a chip off the workpiece and using shear stress as their primary source of energy there. So now the non-traditional ones are going to use some other type of energy out there to create chips or to just remove material. In not all cases are the chips going to be actual chips we can see. In some of these processes we'll talk about, we start to dissolve material atom by atom, and we'll talk about that here. I believe coming in, actually a little bit about that today, but more so on that next class. Now, these non-traditional processes, they have higher energy requirements, and they're slower than the traditional machining processes. So what that means is they're more expensive to go ahead and use on our parts. So it's going to cost more per hour to run parts with these processes or to manufacture parts using these processes compared to those traditional processes. So really, these processes should be reserved only for when you actually need them. So you should always resort to your traditional machining processes first, and then go and look at the non-traditional or maybe abrasive processes if you can't get it done using the traditional ones. So they were developed in a lot of situations where it was just impossible or the process was just incapable or it's impractical to actually produce it that way, or maybe uneconomical. So a lot of these processes were produced because an engineer designed a part, and we had to figure out how to make that part in order to make that machine work. So some of these things, again, were invented thanks to the actual parts they had to go ahead and produce. Now, the non-traditional machining processes are divided into 4 distinct categories based off their energy source. So based off the energy that they're using to remove material from that workpiece, they're categorized that way. We're actually going to start off with chemical and thermal ones today. We're going to talk about chemical, thermal, a little bit of electrical too, and the mechanical ones are coming next week. But they're really divided into those 4 categories where you have some sort of mechanical energy removing the material. You might have electrical energy removing the material. You could melt the material away and have thermal energy remove it. Or we could dissolve it away with maybe acids, stuff like that with the chemical energy. Now there's about 20 different non-traditional machining processes out there. We're gonna cover like the 7 most popular ones out there that are used the most. So we're gonna just cover almost a little under half of them out there. But again, the ones that you might see the most in industry and might design parts as mechanical engineers get processed with these processes. Now, as mechanical engineers, you should know what a heat affected zone is. So if we are manufacturing a part and we put heat into the part above the melting temperature, above the austenizing temperature, It actually doesn't always have to be above the melting temperature. Any elevated heat could actually create a heat affected zone or actually change the properties of the material. But when heat goes into that material and we're manufacturing it, we might actually change the base metals properties through our manufacturing processes. And that's not going to be a good thing, or it might be a good thing. It just depends on what we're doing. So there's something called this heat affected zone. Whenever we melt something or get it really hot, we bring it into that molten zone, right? So we get it the molten state where the atoms are not really like basically organized in a nice crystal structure at this point. They're kind of moving and they're not in the same spot. So there's a lot of energy in there. Things are going on when it's hot. And when that part or the material starts to cool down to room temperature below that austenizing temperature, we start to go ahead and maybe change that structure based off the energy or the heat we put into it. That's really what a heat affected zone is. And I have what we see here is an iron carbon phase diagram. So really this is for all steels and all ferrous materials right here, steel and cast iron. So it has to do with the percentage of carbon content. The more carbon you have, the harder and more brittle the part is, right? So when we get above 2% carbon content, it becomes a cast iron. It goes from steel to cast iron. Well, based off of how we cool that material and the percentage of carbon that we have in that material, we might get different grain structures throughout that. And these are the different grain structures you'll learn about. But when we're above the austenitic range here for steel, let's say we were right up in here in the steel, and we go to quench it. Let's say we had 0.83% carbon content. We go to quench it. We end up with different grain structures in there. And if this happens during the manufacturing processes, we may end up with properties that might hamper our design or might end up causing the part to break or prematurely fail in actual service right there. So you got to think about, are you going to affect this part with a heat affected zone? What, by processing it? So some of these non-traditional machining processes have heat affected zones and some don't. I'd be ready to go ahead and answer which ones have heat affected zones and which ones don't as you go through here. And just realize whenever you're making something, just remember, is it gonna heat it up? Is that heat affected zone gonna go ahead and hurt my metallurgical properties when the part's out in service? You gotta be thinking about that. So hopefully now you understand what a heat affected zone is. In welding, you definitely have a heat affected zone, right? Now, in the first process that we're talking about, there's no heat affected zone. We're gonna first start talking about what we call chem milling or chemical milling. Here with chem milling, basically there's no mechanical stresses or heat affected zones with this process. So this process has really been designed to cut foils or thin materials. So it's ideal for thin metals or thin material. You don't do this on a large chunk of billet here. But so you can basically cut hardened and tempered materials as easily as regular materials. Because what we're doing is we're machining with chemicals or an acid. So there's no mechanical stresses or no heat affected zones. The acid just dissolves the material away. So this is ideal in making really thin metal and foil parts. In fact, you'll see right here on the screen that in the bottom right corner, we have an aircraft fuselage right there. So that thing has been pocketed away to go ahead and have pockets in it. So it's a lightweight fuselage. And we are able to basically lighten up our sheet metal. So if we're able to lighten up that sheet metal, we get better fuel economy on that aircraft, right? Well, this process was originally developed for missile skins. So the skins on the outside of a missile, in order to make it lightweight, they would go ahead and they would pocket that sheet metal out with acid originally. So they would go ahead and be able to create pockets, kind of like you see down here on this fuselage skin. Now, it's used for a lot more than just pocketing into material. If you think about it, like in satellites, they use gold foil to go ahead and act as insulation on a lot of stuff, right? So if we had to go ahead and cut gold foil to a certain shape to insulate something, we wouldn't be able to do it with a mill. Do you imagine gold foil is very equivalent to like aluminum foil? It's not equivalent in price, but it's equivalent in terms of like kind of property, somewhat in mechanical properties. So if I was to go ahead and try to use a mill to cut foil, that just wouldn't work. Think about that multiple tooth cutter wrapping up that aluminum foil. Well, we can machine foils with this chemical milling process. And now the way it works is the chemicals only mill where there's metal exposed. So what you actually have to do before you start applying the chemical or the acid to the part is you have to apply what we call acid resist. So this acid resist is either sprayed on or wet dipped. That's one way. That's in chemical milling. Or it can be put on through a photo tool, a lot like a photocopier. So that would be called the photochemical application. Now, the photochemical application or photochemical milling is a lot more accurate than the wet dip or the chemical milling version of it. So with we're going to talk about both here now. So with the chemical milling, no matter what, there's 4 major process steps here. Number 1, you got to clean your material up and you've got to mask it. So you've got to basically spray something on the surface that chemical resist to go ahead and mask it. So you only have the metal that needs to be removed showing, and then there's a mask over where on the metal where you want to keep. Basically, it's almost having like a stencil on there. So that's what you're doing when you're masking it. You're making a stencil on your part. Now, once the stencil has the acid resist on it, it's either basically dipped or sprayed in chemical milling. The parts get placed in the chemical reagent or in the acid. And what happens is the acid starts eating away on the sheet metal where it's not masked. And you're going to have a little bit of undercut underneath that mask, like you see right here. But that is controllable. You know how long you leave it in the acid and how much etch you actually get. So they basically mask it and they know how much undercut they're going to get at that point. Once you have it in that acid, you go ahead, you take it out and you wash the part off and you have your part, it's completed. So I have some videos on this to show you. This first video right here, just make sure I'm sharing my screen, which we are sharing screen 1. Make sure you can hear the sound. So now what we've got here is on chemical milling, you have to apply that acid resist right there. So this one right here, we're not going to listen to the music. I'm just going to go through it a little bit. So what they're doing right here is they're spraying on the chemical resist. Whoops, I probably should have, you can kind of see it right here. So they're spraying this large piece of sheet metal with chemical resist. Then, whoops, let's go right here. They are taking away the places where they want to pocket out this part right here. So they're peeling off that chemical resist or the mask right there. Now, once they have it all peeled off, they dip it in the acid. So you'll see they're dipping it in the acid, and then there's another bath right there. They dip it in. Then they peel off that acid resist. So what they're left over with is basically a nice pocketed piece of sheet metal right here. You see this? This makes this very lightweight, right? So this piece of sheet metal, this is an ultrasonic transducer that tells the thickness, but this large piece of curved sheet metal is only 77 thou thick, and they put pockets into it right there to make it a lighter weight. So that's a really good example of what chem milling can do. It can go ahead and pocket out your sheet metal parts like you see right there. I could go all the way through, or I could pocket it too, so where it doesn't go all the way through. Really, if I'm through, I don't mask it on both sides. It goes all the way through. If I mask on one side but not the other, it'll go ahead and just make a pocket. It'll only burn down in a certain depth into the part right there. So that's what chemical milling is all about. Now, this video here, give it 1 second to load. So you're going to see these are just the different masks or basically etchants for the chemical milling process. And I just brought this video to show you that they spray it on or they dip it right here. You can see it can be dipped as well, a wet dip process. And now you could either cut it off with a razor blade exactly where you wanted it, or you could use a laser to cut out their acid resist, and it's a little bit more accurate right there. Then you literally just peel the resist off wherever you want to go ahead and etch the part. And then you can see right here, it etches the part down using that acid right there. So it's a chemical milling. We're milling with acids. Now, the photochemical version of this is like a photocopier. So instead of spraying on the photoresist and either using a laser or a razor blade to go ahead and cut out what you want, we can get very exact photoresist copies or stencils of our photoresist placed on the material using a UV light right there. So they have a photo tool now. So what happens here is let me show this video and explain it. But the photo tool is basically the exact reverse image of what they want to go ahead and put on the part. So this is a 3D animation of what's going on in the chemical milling process here. We first start off, let me just turn this off, turn the sound down, I'll talk through it. So we start off with our material, right? So this is a piece of sheet metal. It gets cleaned on both sides. So you can't have any type of fingerprints or anything like that, oils on the surface right there. So we clean that up. We clean the part. It then gets masked right here. So we have the mask goes on the upper and lower surface. Then this is the photo tool. So what happens is you have basically a black and white image of what you want. So whatever's black, it's not going to go ahead and expose, right? So it'll end up being a cutout in the part. Whatever's white, it'll go ahead and expose the material and it won't actually resist or acid resist away. So they're photoresisting there to get a very accurate shape or profile of geometry there. They then get rid of the photoresist that hasn't been developed on the sheet metal. Now we go through the chemical etching stage where it sprays acid on the top surface of that sheet metal. That's going to go ahead and dissolve all that material. So it's removing it atom by atom. And we don't have any burrs. So we've removed all that material. Now at this point, we're ready to go ahead and take off the photoresist. So they have a special chemical that they can spray on the material and that removes the photoresist. At this point, we're now ready to get our product or our parts out of our large sheet right there. So you'll notice they have tabs on here. So the parts don't actually fall out of there. So they'll have to break them off the tabs. Then they have their leftover parts afterwards. So there's all sorts of different parts. If you look back here that they make with that. So if you look, speaker grills, really high quality ones and so forth. So there's all different types of parts you can make with this chemical milling process. Now, this video here is a little bit of a sales pitch somewhat, but it shows you what you can do with the different parts here. So let's watch this one real quick. We're gonna actually.
So the main benefits of photochemical machining over, say, like a laser or an EDM process, it's all thin material, and we don't have any burrs or heat affected zones. The other advantage is when you have, say, a tiny part, that we can lay out that part on this entire sheet.
So look at how many parts they have on that sheet right there. Those would be really hard parts to stamp out because they're so thin. It would have a hard time on a stamping press.
All of it gets etched at the same time. So like a laser and EDM has to individually trace out every single one of these cuts. Where us, we just stick it inside our machine and it all gets sprayed with acid and etched at one time. So there's some major cost advantages over some of the other processes. Hi, my name is Justin Miller, and I'm the sales manager for KeyMac Technology, and we do photochemical machining. This material right here is nitinol. It's a nickel titanium alloy, and we're one of the few etching companies that can process it. It's used a lot in medical devices. And the advantage is it's a super elastic alloy, so you can stretch it out and it will go back to its original form. It's also biocompatible, so it works well for implantable devices. So the other advantage of it is you can heat set it. So you can wrap this up in a circle, you heat it up to 2,000 degrees, and then it will always go back to that form. So for, say, like a stent, they can crunch it up, stick it inside the body, and it will open inside the blood vessel and hold its shape. So this is our etched race car, and right now it's blue because it's got our photoresist on it. And as you can see, the way our process works is we'll coat the material with a photoresist, which is UV reactive. We can then print an image on it using a Mylar photo tool. And once we develop it, it leaves bare metal exposed. So in our process, we put it inside the machines and we can etch all the way through it.
So see, that was made out of one piece of sheet metal right there. They left the photoresist on it, but wherever there isn't any material or there isn't any blue, it went ahead and etched away a little bit of that material. So they etched bend lines into this and everything, so it was easy to bend up even.
The advantage is if you don't mask the backside, but mask the top, we can do a half etch process where we just eat halfway through the material. This can be advantageous for flow channels or putting your part number in the part during our standard process. These things right here are shields. So this material is actually called nickel silver. It's a copper nickel zinc alloy. The advantage of it over, say, a copper is when you use it on a circuit board, you can solder the base material without needing tin plating. The other thing we'll do is we'll put these half etch lines in there, and that's so you can fold the sides up and make a box. So instead of needing like hard tooling, this half etch line will help you get that straight edge so you can get a good 90-degree angle on it. Oh, volumes? We do all the way from prototype up to mass production. We have some
that
customers.
gets you the idea of photochemical milling. Hopefully you understand that process doesn't leave a heat affected zone. It uses acid to go ahead and etch away the material in order to get your pattern that you want. Now, the next one is called EDM. It's a type of music. It's also a manufacturing process. So what EDM is electronic or electrical discharge machining, electronic discharge machining, whichever way you want to call it there. But EDM uses electrical sparks now to erode away metal smoothly and precisely. It's how a lot of your molds are made. So we talked about injection molding last week, right? So a lot of complex molds are made with this process with EDM. Now the sparks can be basically a few thousand sparks per second up to basically 1,000,000 sparks per second you can have. That's a very high frequency, 1,000,000 sparks per second. So now with EDM, there's two types of EDM. There's sinker die, which you're going to see up in the top picture right here, where with the sinker die EDM, this is actually the tool or the electrode. And this is actually the feature that tool burned into the workpiece or into the actual workpiece there. So you'll see they're able to create a tool and then burn that feature from the tool into the workpiece using electricity and sparks to remove that material. Now, in the wire EDM form, that's right down here, it uses a wire, a metal wire. It's like down to 2 thou, 1 thou thick wire, depends on what thickness of wire you get. But it can go ahead and cut out the material out of metal with that wire now. So it's a lot like a hot wire through styrofoam, if anybody's ever done that to cut styrofoam out. But with this EDM, remember there's two versions of that process, right? So there's sinker die and wire. But no matter what type of version we're talking about, it's using thermal energy to that it's going to erode that material away in the exact zone that electrode touches the workpiece. Or there's no touching, it's getting very close to the workpiece. So because a spark is jumping across between the workpiece to the actual electrode, you don't have to have any contact with the workpiece. In fact, you don't have any cutting forces because a spark is actually what's removing the material. When that electrode is maintained between 1/2 thou to about 30 thou away from the workpiece, it'll go ahead and allow, there'll be some dielectric fluid in there. So there's fluid, which will allow the spark to jump the gap. In fact, this is how it works right here. You have a DC pulse. This is happening up to 1,000,000 times per second. Remember this. You have a DC pulse created here. That pulse is in a liquid. So there's something called basically a dielectric fluid. They have almost like a dielectric fluid, but they have a fluid, dielectric, that they put the material in, and the electrode goes down into that fluid. There's suspended particles at that conductivity gap or that field right there, that electrical field. So we get that conductivity bridge forming across that gap. And as the voltage increases, our temperature increases. At a certain point, we end up with a spark channel developing and basically dielectric and the particles vaporize. So basically the dielectric fluid will rush in as the particle vaporizes. And that high temperature spark will end up melting the material. And then the dielectric fluid rushes in and kind of quenches it. So we have a lot of on, off, melting, cooling happening up to 1,000,000 times per second. We're moving material in a slow, controlled manner right there. Now that electrical pulse, once it terminates, again, the spark channel collapses and that dielectric is what actually quenches that material. So because we're going from hot to cold, we have that heat affected zone in here. I'm going to go back a slide. So the cool part is because we're machining with sparks, the material removal is independent of workpiece hardness. It doesn't matter how hard your workpiece is because a spark is actually going to be what's removing through the material. If you've ever done any type of MIG welding and turned up the current too much and burned through your sheet metal, same type of thing that's happening here. This is just controlled in the EDM process. Now, I mentioned there's two types of EDM systems out there. There's the sinker die EDM system and then the wire EDM system. Let's first talk about the sinker die system. This video right here is going to show you how that sinker dies work. It's a little bit older video, but it still at least shows you how that sinker die, how the sinker die EDM is actually going to
Electrical discharge machining, referred to as EDM, is a stress-free form of machining since there is no direct contact between the machining element and the workpiece. There are 3 types of EDM commonly used in today's mold-making industry: conventional die sinker EDM, CNC die sinker EDM, and CNC wire EDM.
It's just all CNC. It's either
conventional die sinker EDM machines use electrodes which contain the detail that is to be machined into the metal workpiece.
So you'll see these are all the electrodes they machined, and then they'll burn that into the workpiece.
Electrodes are made from conductive materials such as graphite or copper. The electrode is placed into the machine. A positive or negative electrical charge is applied to the electrode, and the opposite charge applied to the workpiece. One restriction of the conventional die sinker EDM machine is that the burning can only take place in the Z direction. As the electrode lowers and nears the workpiece, an electrical spark jumps from the electrode to the metal. This spark burns the metal, and dielectric fluid is used to flush out the burnt pieces, allowing the electrode to burn uninterrupted until the desired depth is reached. When the burning is complete, the result is an impression of the electrode in the metal. The distance between the electrode edge and the burnt metal is referred to as overburn or spark gap.
So the rest of this video talks about what overburn is. So what they're getting at is you have to make your electrode a certain percentage smaller than your actual feature, because when the spark jumps the gap, it's overburning or making the actual feature larger than the electrode. So there's an overburn percentage based off the current and frequency you're running, and you know how much to undersize your electrode, because the part then will become oversized right there. So if you want to watch the rest of that talking about overburn, you have the link right there. But I want you to, what I really wanted you to do is understand what sinker die is compared to wire EDM. Now, this wire EDM uses a conductive wire. Materials have to be conductive in EDM, but it uses a wire now to cut the part. Look at the size of some of these parts. There's a paper clip right there. Look at the size of the cutouts and what you can do with wire EDM. It's probably one of the most, I don't want to state that. So I was going to make a statement.
Making parts with highly detailed, extraordinarily tough.
What I was going to say is it's probably one of the machining.
Nearly impossible with conventional machining.
It was one of the machining processes where you can make really intricate parts. I wanted to say you can make the most intricate parts with it, but I don't want to say that. You can make very intricate parts with this though. Look at the size of this, right? Got that dime, and then look at the size of these parts and these cuts right here.
Techniques, but not with a wire EDM process. Imagine being able to make precise cuts in metal with a blade no thicker than a human hair. That's what wire EDM can do. EDM stands for electrical discharge machining. But instead of a blade like a bandsaw, wire EDM uses an electrically charged hair-thin wire to remove microscopic particles and shape the part. These animations help show how wire EDM works. The wire carries one side of the charge, conductive material carries the other side of the charge. And when the two get close, a white-hot electrical spark jumps the gap, melting away tiny dust particle-sized pieces of metal, 2 microns or smaller. How small is a micron? Well, if this was the diameter of a human hair, this would be a micron. But what's all this liquid? Well, that's the dielectric. Deionized water, really, useful because it doesn't conduct electricity. In wire EDM, the liquid dielectric controls the sparking, cools the process, and flushes away those tiny particles as they're removed. All very fast, about 1 million sparks per second. The particles themselves are each about the size of a particle of smoke. In the right hands, wire EDM can be used to hold really tight tolerances, create incredibly complex shapes, work with difficult materials that may be extremely hard or soft, and if needed, make really, really small parts. There's even something called small hole EDM for working from the inside of the hole to the outside. All completely automated and CNC controlled. No human involvement. At Exact, wire EDM is all we do. We're very good at it, making us the perfect wire EDM partner to produce complex precision parts.
Look at the cutouts in that part right there. So look at some of these parts that they do. Well, this one looks like one part, but it's actually 2. It's because the wire is only 2 or 3 thou thick. It's the thickness of a human hair to cut it out.
That often can't be made any other way. Like this. Looks like one part? It's really two. And this springy thing is just one part. Want to see more? Watch more of our videos or...
So that's the wire versus sinker die. Now with this EDM process, it creates a heat affected zone. I mentioned that. So we have what we call a recast layer on steel workpieces where the sparking occurs. So you have a very smooth surface. You just got to be careful because if you have martensite on your sinker die EDM surfaces right there. So if you see a lot of thermal expansion and contraction, you might get cracking on the surface of your parts. Or if it goes to a really cold location, then gets really hot again, you just got to watch that out. Watch out for that in your process. But if you look right here, here's an old cell phone. So back in my day, when I was your age in college, this is what our Nokia phones look like. We called it the Nokia brick. But this is what the cell phones used to look like, right? But this is the wire EDM electrode, or this is the sinker die electrode. And then this is the mold that it went ahead and burned down into the mold. So hopefully you can see after learning about injection molding, how this is a very important process for manufacturing molds. So the wire EDM now will actually cause the surface to maybe get softer. So carbon's extracted from the recast layer rather than added to it because it has to do with the water, right? The deionized water. So sometimes the wire surfaces might be a little bit softer and you got to just watch out for that. So if you look right here, this looks like one part, but when you slide it apart, it's two parts, right? It's pretty impressive though, the depth of these little small cutouts. You can't do that with any other machining process we've talked about. Now, some advantages for EDM, there's no cutting forces. So I can cut hardened tool steel molds as easy as I can cut aluminum molds. That's a big bonus. And you can get high aspect ratios. What I mean by that is you can go from this ratio up here and all the way down to this other shape afterwards, right? You can get very intricate cavities. You can almost have a perfectly sharp corner. I mean, if your wire's 1 thou in diameter, it's a 1/2 thou radius in the corner. That's almost perfectly sharp, right? I would call it perfectly sharp. And it's unaffected, so it's unaffected by material hardness. You can see they cut these gears out of this hardened steel right here very easily, where they had to just drill a hole first to feed the wire through. Then the wire takes off and cuts that all in basically one move. And the wire is continuously spooling, by the way, and you can only use the wire one time. So the wire is either made out of tungsten or copper, depends on what your alloy is that you're cutting. That wire, that's what makes it such an expensive process. The wires are consumable. Those electrodes are all consumables. So that's really the disadvantage, is the high capital cost right there and a consumable electrode. So we have to be able to keep machining electrodes and keep getting wire in order to keep this process going. Now, if you look, here's some tire molds. So this is a Continental tire mold. You see that right there? So the wire EDM the sinker die EDM was able to sink in the wording into this tire mold and this little, I guess it would be a tread. And then you can kind of see here's another tread out here on another piece of a mold. So they're used heavily in mold. Now, a disadvantage, you can't do it on polymers. It's got to be an electrically conductive workpiece. It's not a very fast process whatsoever. So it's got a low material removal rate, and you've got a heat affected zone you may have to worry about, or it may not even be a big deal. So that's what EDM is all about, electronic discharge machining. Now, the third one we're going to talk about this week is what we're actually going to be doing in lab. We're going to be laser cutting. So with laser cutting, we're using optical energy and converting that to thermal energy on the surface of the workpiece. And what we're doing then is we're focusing and we're melting that metal right at a controlled manner. So we're melting metal in a controlled location, a really small location, the size of the laser beam, whatever that diameter may be. Now, it does not require a vacuum, and you can machine metallic and non-metallic materials with a laser cutter. So what we're gonna do is we're gonna machine cast acrylic with our laser cutter. And so it's basically, it vaporizes the material in a very small, well-defined area. So what you're seeing are basically the particles or the chips coming off this laser cutter as it's vaporizing the material. Now, these laser cutters, when it focuses the laser beam on the surface of the part, the height really matters. The height has to be set so the focal length is right at that top surface of your material. What it does is when the focal length is focused right at that top surface, it melts a really small keyway, or basically keyhole area. Then a lot of laser cutters will have a gas assist where they blow pressurized gas or pressurized gas out of the nozzle in order to have the vaporized material blow out of the keyhole. That's all you're seeing is that material just get out of the keyhole for the actual cut right there. Now, our diameter or our tool's diameter could be up to 1 thou in diameter to 20 thou. Most of them aren't 1 thou. Most of them are bigger, like 10 to 20 thou for the diameter of that laser that it's going to cut. Now, this video right here talks about how that laser beam actually creates the laser. So what it's doing is a laser is basically light amplification by stimulation of photons. So we're stimulating photons. I'd just like you to understand how the laser actually works before we go on. So here it is.
A laser beam is basically radiation, similar to light that a light bulb emits. There are 3 big differences. The light bulb emits several wavelengths, but the laser has only one wavelength, meaning it is monochromatic. The light bulb radiates in all directions, whereas the beam of the laser is directed. The laser light is coherent, so the wave trains are much longer than those from a light bulb. But what does laser mean anyway? Laser is an acronym for Light Amplification by Stimulated Emission of Radiation. Sounds complicated at first, but actually it is not. A laser consists of a laser medium, for example, a gas, an energy source, pump, and 2 mirrors, one of which is partially transmissive. The laser medium consists of particles that are in their basic state. The pump feeds energy into the particles, and they rise to a higher energy level. If any of these particles then falls back into their basic state, energy is released in the form of a photon, also called light quantum. If this photon then hits another excited particle, then it's forced back into the basic state, releasing another photon. This is referred to as stimulated emission. If these photons hit other excited particles, then further photons are released, and so on. A sort of photon avalanche is triggered. Energy is repeatedly pumped into the laser medium, stimulating the particles so that they can release more photons. The mirrors reflect the photons, thereby increasing the number of photons further and further. A directional beam is formed. This beam can leave the laser through the partially transmissive mirror and is directed onto the material, where it engraves, marks, or cuts the desired motif.
So that leads us to what lasers do in machining and manufacturing. So within that manufacturing world, lasers are either used to cut material, mark surfaces, weld, or heat in exact locations. So what we're going to use it for is we're going to cut and we're going to mark surfaces. So we're going to do some laser engraving and some laser and cutting on our Geneva wheel in lab. When you have, what is that? We're going to be week number 3's live lab. So, or day number 3 when you're in your face-to-face lab. So week 6 or so for you. So this video right here, whoops, here, I just want to show it to you real quick. Now, this one's a how it's made video on laser cutting machines. We're not going to watch the full how it's made on laser cutting machines, but I thought it would be nice.
What's your baby's favorite?
We're not going to
toy?
watch that right now, but so it's a 5-minute video on how laser cutters are made. Definitely check it out. It's pretty cool. It shows you how they machine the actual tube, the vacuum tube where they fill that with CO2, and then they actually are generating the photons, the laser tube. And then they show you how they calibrate it as well by basically burning acrylic, big chunks of acrylic. Check that video out. But lasers, those photons, are really made 3 different ways out there. So basically we have fiber lasers where they create those photons through banks of diodes and through fiber optic cables. They have YAG lasers. So that uses a crystal as basically a lasing medium right there. And those are the higher power lasers, might use a YAG as their actual photon generator. They cut steel and other metal alloys. Now, our lasers at Cal Poly aren't very strong. We have CO2 lasers, and our CO2 lasers, our 75-watt one won't cut metal. It doesn't have enough power to cut metal, but it cuts through acrylic. It can engrave an acrylic, and it's using they do have CO2s that cut metal, don't get me wrong, but ours isn't very powerful to cut metal. It's a cheaper laser. It only costs about $30,000, where some of those lasers that are going to cut metal will be 60 and up and upwards, up into the 500s and so forth. So what I want you to know though is these are the three different mediums or the ways that they generate the laser beam right here: CO2, YAG, and fiber. So the cool part about this laser cutting is the laser beam never gets dull, and there's almost no limit to the cutting path. So it's a forceless process. I can just place the parts down on the table. That laser beam's always sharp, as long as the CO2 doesn't leak out of our basically photon generator. So that's the only thing, that's the only way it could really go bad, is the laser medium piece gets a leak in it and it has to then be rebuilt, or you have to get a new one. So they cut at very high speeds too, these lasers. So it's really based off the material thickness. The thicker the material, the slower it cuts right there, because it's got to take that time to burn down through the whole material. So when I click on this video right here, this is showing you a very fast laser cut. So this is one where it's a pretty thin material, probably like 8 gauge. No, it's probably less. It's probably higher than that. It's probably like 15. Pretty thin. So if you look right here, what it's doing, I'm gonna get it going here. It's cutting. You always cut whatever drops out last, the outside profile, right? You got to do everything inside first, then you cut out the whole outside profile, because really the laser cutter just sits on the machine as a big sheet of sheet metal. It sits on like a nail, they call them a nail bed. It's a bed with basically just pins sitting up there. So what you end up doing is you're not cutting the bed, you're just cutting the sheet metal right there. So you're gonna see they're dropping their cutouts out of this thing, and that's a pretty fast cut if you think about it. Now I'm gonna move down here a little bit more. You can watch the video, you have the link. You'll see this is like the back of a computer, right? Or like if you look at the back of like a PC, a desktop, they have all those different cuts, and there's the hole for the muffin fan and so forth. As we kind of go through here a little bit more, you can see there's the part, and then they're finally cutting out the outside last when you're all done. So then the part falls out and you have your laser cut part ready to go into that assembly. So now this one right here shows you some thicker material too that these laser cutters can cut. I wanted to just show you this one. Give it 1 second. For some reason my internet's super slow today. That's weird. So, oops, now don't look at that. That's an ad. There we go. So this laser, this is a very large laser. This is probably definitely a $500,000 laser, looking at the price, the size of this thing. So what we got here is it's going to go to the real laser right here. This is 10 millimeter, just kind of shows you the speed on 10 millimeter. Stainless steel sheet right there. Now they're going up. There's 16 millimeter. Notice it's a lot slower. That's what I was trying to get across to you, is it's really based off the thickness of the material of the plate right there. So that's another example in 16 millimeter. Now, oh, there's some really thin stuff. It's going really fast. Where was they had like 1 inch thick plate. Hold on. It had a big plate somewhere. Oh, it was at the end. It just kind of showed you the thickness of some of the parts that you could produce on the laser cutter right there. So you can check out that video. It's a 20 kilowatt. So we only have a 75 watt. This is 20 kilowatts, right? Fiber lasers. That one's a fiber laser. We talked about the different ways they generate their laser. Now this one, last one, is a 5-axis laser cutter cutting unibodies for automobiles. So what this is doing is, if you have a bulk deformation, right? You have a stamping. So you have your sheet metal stamping, and you've got to trim it before you put it into the automobile and put the holes in it where it needs to go. But you'll see a lot of this material, it was held there just for the stamping operation. You got to trim it and get rid of it. So what this laser cutter is doing, it's trimming the automotive, basically unibody stamping. So then you can put them together and spot weld everything together and have your automotive frame. So you'll see it's just about done cutting out everything it would need for the frame rail, or I don't know exactly what that's to, but it's like a frame rail for an automobile. But then when it's all done, check this fixture out. It comes around and it trims it. The fixture's automated. That's pretty cool, right? It's coming around and cutting out the overall profile. Then we can go put that together in the assembly and put it all together and make an automobile, most likely. It's how cars are made. If they don't have a frame, they're all just stamped sheet metal pieces that have been laser cut like that. So that's laser cutting. I don't have a video for you this week for laser cutting, because you're going to go in and you're going to do this in lab step by step. where you're going to learn how the raster and the vector functions are different in a laser cutter. And you're going to go through, use a DXF profile, and you're going to learn how to cut these out in groups of basically, they come out in groups of 3. So you're going to get into groups of 3 in your lab, open up, program the laser, and make this part like you see right here. So this week it was a little bit shorter than normal, but again, you probably have midterms for other classes. So 45-minute lectures, probably not too. 15 minutes, missing 15 minutes here or there is probably not too big of a deal. If you have any questions, either shoot your lab instructor an email, stop by their office hours, or you could shoot me an email or stop by my office hours. Hopefully you've learned a lot about the non-traditional machining processes, at least 3 of them today, and why they're important. When we can't get it done with traditional, we go to non-traditional, which doesn't use shear stress. That's the key, right? They're going to use other types of energy to remove material. Now, next week, we'll get into some of the other non-traditional machining processes like water jet. And then there's another one. There's ultrasonic machining. It's how we can machine glass and ceramics. So there's some cool things coming up. Then the week after that, we'll do abrasives. So have a great week, everybody. Enjoy making your Geneva wheels in your face-to-face labs. I believe you're probably injection molding this week. So enjoy that injection molding. Have a great day. Talk to you later.